So far we have assumed that when you apply a sine wave voltage to a single phase transformer, the flux in the core is sinusoidal and the current drawn by the transformer is also sinusoidal. However, in practice this is not the case. This is mainly due to the nonlinearity of the magnetic core used in a transformer, which are made up of ferromagnetic material. So, a practical transformer, you will have a core on which the windings will be placed and on the other winding the load may be connected. The applied voltage we assume to be sinusoidal. If we neglect the resistive drop in the winding, then the counter induced EMF must completely cancel the applied voltage, that is the counter induced EMF E should be equal to VI. Hence, the flux which is given by N1 d phi dt equal to E will be equal, this will be sine wave. So, the flux in the core will be sine wave. And the flux will also lag the applied voltage by 90 degree. Now, had the magnetic material been linear, the current drawn, the magnetizing current drawn by the transformer would also have been a sine wave. However, this is not the case in a practical transformer. In a practical transformer, the no load current, the magnetizing current and the flux are related by the BH characteristics. Of the material. Due to this nonlinear BH characteristics, we will soon see that the no load current drawn by the transformer will not be a sine wave, but it will be distorted with different harmonic components. Let us examine this a little more carefully. Let us say this is the applied voltage waveform. The applied voltage waveform VI, and the flux waveform which will lag the voltage by 90 degree be somewhat like this, the core flux. Now, let us try to find out what will be the current due in order to establish this flux in the core. For that, we will have to consider the BH characteristics of the material. So, for the current, let us see that at time t equal to 0, when applied voltage was 0 and increasing, the flux was at its negative peak. This was the value of the flux, and hence the corresponding current was this. So, current was at negative maximum. Let us say this corresponds to the negative maximum of the current. Now, as the voltage is increased, now flux is increasing, and while increasing in a BH curve, the flux follows this path. So, we see the current when the current becomes 0, the flux still has a negative component, that is, the current will become 0 before the flux becomes 0. So, this is the point, let us say, where the flux will become 0, where some current still exists, some flux still exists. When the flux becomes 0, we find that the current has become already small positive. So, this corresponds to the point. Again, when the flux reaches its positive peak, which coincides with the 0 crossing of the voltage, the current also reaches its positive peak. So, this is the corresponding point of the current, and since the BH curve is symmetric around x axis, the positive peak of the current waveform and the negative peak of the current waveform will be equal. While returning, though, the flux takes a different path because of hysteresis. So, we see that when the current becomes 0, the flux still has some positive value. Therefore, the corresponding point here will be, let us say, this, and when the flux becomes 0, the current has already become negative. And here it is again negative peak. Therefore, the current waveform will look somewhat like this. Which is not sinusoidal, although it is symmetric around y axis, but it is not sinusoidal, unlike the applied voltage waveform Vm Vi or the flux waveform phi m. So, this current waveform is not sinusoidal. Of course, it can be divided into Fourier components. It will have, so the current drawn I m will have a fundamental component I 1 m plus harmonic components, and because of its odd nature it will have only odd harmonics, that is where I 1 m equal to I 1 m sin omega t cos omega t plus sin omega t plus phi, and I n m equal to I n m sin n omega t plus n phi. So, this is the source of, mostly the source of harmonics in a single phase transformer, and mostly in the magnetization current that this harmonic will be observable. There is one interesting thing to note here, that the zero crossing of the flux waveform and the current waveform do not coincide. In fact, the zero crossing of the current waveform leads the zero crossing of the flux waveform by some angle. Although the peak of the current waveform coincides with the peak of the flux waveform. If one decomposes the current waveform into its Fourier components, at the fundamental we will find that the current waveform has a component which is a large component which is in phase with the flux waveform phi m, and a smaller component which is leads the phi m, and in fact it is in phase with the supply voltage Vi. So, the out of phase, that is the component of I m which is in phase with phi m and in quadrature with Vi, that is at 90 degree lagging Vi, is responsible for setting up the flux in the core, while the in phase component of I m, that is the component which is in phase with the applied voltage Vi, supplies the hysteresis loss. Of course, this magnetization current waveform will also be modified by the eddy current component. However, this component is sinusoidal because the flux is sinusoidal, which introduces a sinusoidal voltage in the core and sinusoidal current in the core material, which will be compensated by drawing sinusoidal current from the source, which will be again in phase with Vi. So, the in phase component, sinusoidal component of Vi will increase, that will make the waveform less distorted. Therefore, the no load current of a transformer will have a in phase component which is due to in phase component which is in phase with the voltage, which is due to the hysteresis and eddy current loss, and a component which is perpendicular, which is lagging Vi by 90 degree and in phase with the flux waveform, which establishes the flux. In addition to these two fundamental components, there will be harmonics, odd harmonics, that is third harmonic, fifth harmonic, seventh harmonic, etc., of the fundamental frequency, which are due to the saturation of the core material. The deeper into saturation the transformer works, the more will be these harmonics, and the nature of the current waveform will become very peaky. However, when you, since the magnetization current is non-sinusoidal, one would expect if one assumes the winding resistance that the applied voltage is sine wave, the current drawn I0 has harmonics, then one should expect the induced voltage E also to have harmonics. Hence, even the flux wave form will possibly not be exactly a sine wave, which may or may not increase the harmonics in I0 depending on the nature of the BH characteristics. However, since I0 magnitude is very small and also the stator resistance is small, E and phi m can be for all practical purpose assumed to be sine wave. So, in a transformer, if the applied voltage is sinusoidal, then the core flux is almost a sinusoid, but the magnetization current drawn is distinctly non-sinusoidal. It has fundamental components and odd harmonics. However, when we put a load on the transformer, I have already mentioned that there will be a reflection current IL dash flowing in the transformer. Since the core flux is a sine wave, the induced voltage on the secondary side is also a sine wave, and if the load is a resistive or inductive, a linear load, then the current IL will be a sine wave, and hence the its reflection IL dash will also be a sine wave. Now, I0 is much smaller in a normal transformer, I0 is much smaller compared to IL dash. So, when a transformer is loaded, IL dash will dominate over I0, therefore, the waveform will look very much sinusoidal, and although there will be harmonics of the magnetization current present, but it will not be apparent since the magnetization current constitute only a very small fraction of the total put current of the transformer. So, a transformer, single phase transformer at no load draws a non-sinusoidal current from the supply consisting of fundamental and odd harmonics. However, on load, the fundamental component also include the reflected load current. So, the fundamental component increases, but the harmonics do not increase. Therefore, on load transformer current appears to be more or less sine wave. At this point, one should be careful about how one should connect a transformer for performing certain test. In this circuit, we have assumed R1 to be small. However, suppose we want to perform a no load test on this transformer and the available supply voltage is larger than the transformer voltage rating. Then one possibility could have been to connect the transformer like this and then connecting a resistance of a large value and connecting the transformer across the supply. Since we are doing a no load test, then the current drawn by the transformer will be non-sinusoidal and the voltage, actual voltage across the transformer will also be non-sinusoidal. This will make the flux non-sinusoidal with predominantly third harmonic component. The flux waveform, instead of looking sinusoidal, may look something like this. This is the sine wave component of the flux. This is third harmonic component of the flux. So, the resultant flux waveform may show predominantly peaky nature if additional resistance is connected here, in which case because of saturation this will be significantly higher than the fundamental magnitude of the flux. So, the current drawn by the circuit may be significantly large. Therefore, it is not desirable to make a circuit connection like this. Hence, for doing no load test under such a situation, it will be preferable, instead of using a resistance to drop the voltage, one should use a auto transformer variac in order to reduce the voltage to the desired level. Because the induced voltage in the auto transformer will be almost sinusoidal. So far, in this figure, we have assumed that the transformer is operating in steady state, that is, the given a sine wave applied voltage, the flux waveform is also a sine wave. However, when the voltage is first switched on in the transformer, it undergoes a transient before the flux settles down to its final sine wave value. During this period, the transformer can experience very large current. Let us see how. Again, this is the transformer on no load. If we assume that neglect the transformer winding resistance, then we can write E equal to N d phi m dt equal to Vi equal to V sin omega t, or phi m equal to V by N minus V by omega n cosine of omega t plus and constant of integration. At time t equal to 0, one would expect that the core is de-energized. So, phi m at time t equal to 0 may be assumed to be 0. So, at time t equal to 0, or C equal to V divided by n omega, or therefore, phi m assuming at t equal to 0 the voltage was 0, phi m will be V by n omega 1 minus cosine of omega t. Let us plot this. So, this is the applied voltage V sin omega t, applied voltage V I. We have switched it on at t equal to 0 when the voltage was 0. Then the flux waveform phi m is given by of the form phi m equal to phi max into 1 minus cos omega t. At t equal to 0, it was 0. At omega t equal to pi by 2, it will become phi max, and omega t equal to pi, it will become 2 phi max. So, the flux waveform will be a cosine wave which is phase shifted by phi max. Now, let us see what will be the consequences in terms of currents. As we have already mentioned, a practical transformer core will exhibit a predominant saturation characteristics along with hysteresis. Let us say a transformer is usually designed to operate at a flux density of phi max, maximum flux of phi max. However, we see that because of switching initially the flux rises to almost double the value. Due to nonlinearity of saturation, the current will not be double, it will be very large. In cases it can be 50 to 100 times the normal no load peak current. So, the current waveform, as we see at, if we neglect the hysteresis at t equal to 0, it is 0, at phi m reaches its, at omega t equal to pi by 2, it reaches this rated value, and then at omega t equal to pi it reaches a very high value. And this waveform repeats. So, if we look at a large scale time scale, we will find right after switching the current rises to very high value and is almost entirely positive. It does not become negative initially. Then slowly, because of different losses in the core, the flux slowly gradually reduces and settles down to its final value. Accordingly, current also gradually reduces. So, the first peak can be, as I said, 50 to 100 times the normal steady state peak magnetization current, which means it can be 5 to 10 times the full load current of the transformer for first 1 or 2 cycle. This is called the inrush phenomenon in a single phase transformer. This occurs due to the depending on the wrong switching instant of the voltage. It is interesting to note that instead of switching the waveform, the voltage at 0 crossing, had we switched it at the peak value, that is if the at t equal to 0, if I switched it at the peak value, then Vi would have been given by, instead of V sin omega t, it would have been equal to V cosine omega t, that is equal to V sin omega t plus pi by 2. In which case, that is if we would have switched on at the positive peak, then the flux waveform would have been phi m would have been and if at t equal to 0 phi m was 0, then C also would have been hence the phi m waveform would have been equal to V by n omega sin omega t equal to phi max sin omega t, and there would not have been any inrush phenomenon. So, depending on when the transformer is switched on, it is possible that there will be a magnetic inrush in a single phase transformer, due to which the no load current of the transformer can rise to dangerously high level for initial few cycles. The protection system should be designed to handle this, because it is difficult to precisely determine exactly at which instant a transformer will be switched on. The situation will become worse, since a transformer at t equal to 0, the flux in the core may not be 0, because of previous excitation of the transformer, there may be some flux remaining in the core. This is called retentivity. So, if you have some remnant flux in the transformer, then the peak flux density may increase even more than twice the steady state peak flux, in which case the peak of the inrush current will also increase accordingly. On load though, this effect becomes somewhat less, because the flux decays fast and the peak value of the current reduces faster. Therefore, in a single phase transformer, a switching transient during turn on may cause magnetic inrush, due to which the no load current can increase to very high level. This current slowly decays because the losses in the transformer, and finally settles down to the normal magnetization current. Thank you.